Hello everyone and welcome to We Meet at Digital Days. My name is Marie-Therese Kohl and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is high-frequency three-phase PFC solutions for high-power charging stations from our partner ST Microelectronics. Our speaker is Francesco Gennaro. He will hold the presentation and will answer your questions. But before we start, I would like to point out one thing. You will be muted during the presentation. This means that you cannot ask questions via microphone during the presentations. Nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. You will find the chat function in the control panel. This presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email afterwards. If you still have any other questions left, just mail us at exhibition@we-online.com. We will try to answer all questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve our event. You will also receive the link to the presentation in the next few days. The recording will be available at our website shortly. But now I will hand over to our speaker, Francesco, and I wish you an exciting presentation.
Good afternoon. My name is Francesco Gennaro. I'm Application Manager for Power Conversion Development, and I work in System Research and Application Group in ST Microelectronics. Today, we will discuss about high-frequency three-phase PFC solution for high-power charging station. With a very short agenda, we will give a look at the charging station as a general, power factor correction, a short view of semiconductor technologies which are interested in this application, and a focus on a specific topology, which is a bidirectional PFC named three-level T-Type converter. Then we'll go to conclusion. Charging stations, are the very companion of car electrification, and they are really impacting on the grid infrastructure and management. In this presentation, I will go to a building block of a charging station, in particular a DC charging station, looking at the active front end, which is the interface of the charging station with the grid itself. In this case, due to the interface functionality, power quality performance are very important, as well as efficiency and size of the charging station itself. Several power converter topology for high power are available and will be considered in terms of efficiency and performance, with a specific look at the introduction of the new technology, semiconductor technology, which is based on silicon carbide. Charging stations are basically energy-driven application, and we can see which is the trend towards 2030, and we are going up to 280 billion kilowatt hours with a number of chargers which is increasing everywhere in the world, from US, Europe, and China as well. And the investment plan, as we can see from the source of this study, which is McKinsey, up to $50 billion by 2030. The charging station as a DC fast charger has basically two blocks. The first one is interface with the grid, which is the PFC, or the power factor corrector circuit. And then there is a second stage, which is the isolated DC-DC converter, which is providing the regulated current to charge the battery of the car, for example. Giving a look at the specific or the three-phase PFC, of course, we have availability of power technologies for the switches, and we need also some signal conditioning and the control section And basically for this application, just microcontrollers, standard microcontrollers are available and are able to drive the application. Shortly on power factor correction, as I said, the front-end converter is the power electronic stage, which is in charge of controlling the input current, making the power converter behaving as a resistor. So basically having the input current in phase with the voltage and drawing a very sinusoidal current. This is important because this is impacting the quality of the grid and also the losses that we can feature on the grid. So two main factors, two main figure of merits are important in terms of power factor correction, and are the power factor itself, which is a number, but also the total harmonic distortion, which is a measure of the number of harmonics that are inside the current that we are drawing from the grid. In Europe, for example, there is a specific standard which is driving and regulating this harmonic distortion and all the behavior of the power factor correction circuit. Giving a look at the history, this is the very first three-phase PFC, very simple, which consists of input inductors plus a three-phase diode bridge and only one active switch, which is regulating the input current. Of course, this was not performing the best for this application, but it was just the first starting point for the new application. Total harmonic distortion was not the best, was still quite high, but this was as I said, this was just the beginning of the history. And this was a second step, still for the three-phase, where after several studies, we came up with a very simple topology, as we can see here, and it's called as a Vienna rectifier, where basically the three-phase converter has been optimized with bidirectional switches, and in addition with a three-level modulation, which is able to stress the device with half of the output voltage. And this is more and more important as the output voltage is increasing. So in particular, for charging station where a typical DC bus voltage is in the order of 800 volts, more or less, it is important to have reduced voltage across the switches, because this will save a lot of switching losses. There is also another approach to the three-phase solution, which is a modular approach starting from single phase. This solution is allowed to have three single-phase modules with a single output, which could be operated even in parallel in order to improve to enlarge the available power. These topologies and this architecture are really suitable where there is a possibility to supply the charging station even with a single phase or with a directly three-phase voltage. So I would say that the three-phase modular approach with a single-phase module is more suitable for onboard charging. But is going also to introduce in order to reduce the industrial cost also for the three-phase system for charging station itself. Semiconductor technologies, which are very important in this field because they are enabling the development of new structures and increasing also the performance of the solution. So just to give a look at what is available on the market from semiconductor supplier and dividing the overall scenario in terms of frequency and output power, we can see that charging stations are more or less positioned in a power range above 10 kilowatts. So let's say starting from 22 kilowatts up to some hundreds of kilowatts. Of course, the 100 kilowatts application is more and more modular with some basic building block in the order of 30 or 50 kilowatts. In the same area, in terms of power semiconductor, we can also position the silicon carbide, both for diodes and MOSFETs, since this technology is providing at very high frequency and high power superior performance compared to other semiconductor technologies like silicon in this case. There is also a small part for GaN, but of course this is limited with for lower power application and higher switching application itself. So for the charging station, I would say that semiconductor of choice is the silicon carbide. And this is a short story of silicon carbide from 20 years ago till now, with the continuous shrinking of the size of the die and the superior performance, which are more and more improving in the last year. So also in terms of adoption in the market, there was in the last 3-4 years an increase of more or less 30 times from 2017 to today. The selection of this semiconductor technology is not only for a lower voltage class, which means 650 volts, but it's also available for 1200 volts devices. And this is where silicon carbide is providing the best performance and the best benefits for the overall application. Also because silicon IGBTs is a counterpart in terms of semiconductor technology, so in terms of silicon. And of course, there is no real substitution of silicon carbide of the silicon for IGBTs, but it depends on what is the final aim of the application. If we would like to have high power and high efficiency with no cost relationship, so then silicon carbide MOSFETs can be considered for sure. On the other side, if we need a balance between cost and performance, still silicon IGBTs are the device of choice. I will show later which could be the benefit of using one or the other technology. SiC benefits and advantages, which are really summarized in these slides. So higher performance and voltage operation, so extremely low power losses, high efficiency at low current, and there is also the intrinsic SiC body diode, which is able to provide 4-quadrant operation. We can increase operating frequency with lower switching losses and switching performance of the diode as well. And there is an additional factor which is really important, which is the operating temperature that we can extend due to the wide bandgap material characteristics up to 200 degrees Celsius in terms of junction temperature. Of course, also the package has to sustain this high temperature. So there is not only semiconductor, but is also package. So there is an overall efficiency gain in a typical application with lower switching losses, more or less 1/10, with 1/5 of chip size. So also the size can be reduced, and the total losses reduced by 50% at a switching frequency, which can be 10 times higher. So of course there is no single answer to the question of the selection, but of course is as usual is a trade-off between performance, cost, size, and overall design. As I said, there is a very strong link between the technology of the semiconductor and the package. So in order to get the best benefit from this superior technology, we need also to have a suitable package in order to manage basically thermally the final device. And also for silicon carbide has been developed some specific package, which is a single dual die packages like the HU3 pack and the ST pack, which are for very high current application thanks to the superior thermal performance. When the discrete approach is not enough in terms of power, then the module, the low cost and very simple module that we call ASPEC or ASPEC 1 or 2 or ASPEC SMIP can be used in order to have a multi-die power modules. Just to provide you a very simple comparison between silicon carbide and silicon. So basically silicon carbide MOSFET and silicon IGBTs inside the module, we can see that from a simple exercise, there will be a reduction of 10 times compared to silicon IGBTs thanks to the reduced size of the die. And in terms of performance, if we give a look at the efficiency graph here for silicon carbide MOSFETs, we can achieve more than 3% of efficiency gain compared to silicon IGBTs. It is important also to have a very a good selection in terms of topologies in order to reduce the size of the overall converter. So the typical building block for the converter, like the half bridge, the full bridge, or the 6-pack full bridge are available in the market, as well as the 3-level T-type leg, which is very common in this kind of application. Which is the real importance of the package technology? It is important basically for 3 aspects. The first one is from an electrical point of view, because we can reduce the internal connection layout, so we can reduce the parasitics inductance of the connection. We can improve the overall layout of the board, so this will lead for sure in a reduction of the noise around the circuit and in improving of the switching losses, so the efficiency of the converter. There is also a thermal aspect, since the module is much easy with the module is much easier to dissipate the heat from the circuit, and also to manage the overall thermal aspects of the application, which is quite easier since it's concentrated in one module. And going back to electrical aspects, the noise and the disturbance around the circuit, which are included inside the optimized layout of the module, will be reduced. So the overall EMI of the circuit will be improved using this package. Let's go to simple PFC topologies. So the 3-level topologies are being summarized in 2. So Vienna rectifier type 1 and type 2 as a basic comparison between the 2 topologies. The main difference is that in type 1, we can use only 650 volts devices. So we do not need any very high voltage device, even if the output voltage is up to 800 volts or 900 volts. Since it is a 3-level topology, and the voltage across the device will not see higher than half of the output DC voltage. But there is a disadvantage, which is related with the current path, that we see always 2 switches in series, 1 diode and 1 active switch, with a slightly lower efficiency, which is not the case of the type 2 Vienna rectifier, but there is the necessity to use 1200 volts devices. Or in this case, for example, D2 plus and minus are 12 volts 100-volt diodes. Giving a look at a comparison between the performance of type 1 and type 2 converter and spanning the frequency between 20 kHz and 80 kHz, we can see which is the difference between the 3 main semiconductor technologies. The first one is the silicon IGBTs in red, in green the super junction MOSFET, so still based on silicon technology, and the blue one is based on silicon carbide MOSFETs. For the 2 topology, we don't see a very big difference when the switching frequency is quite low for a given device. But as soon as we increase the switching frequency and we approach 100 kHz, which can be something feasible for this kind of application, we can see a small difference in terms of efficiency in the order of 0.2, 0.3%, which is nothing for 1 kilowatt application. But if you consider 50 kilowatt application, this means a lot of energy that can be dissipated. For SiC Enabled Topology, what does it mean? It means that thanks to the introduction of silicon carbide technology, some topologies that are not able to be used with superjunction MOSFETs or with in general silicon-based power transistor are again valid also for very high power and high switching frequency. This is the case of Vienna rectifier type 2 with input diodes using silicon carbide diodes, and also for the bidirectional Vienna rectifier, which is an evolution of the type 2 Vienna rectifier, just replacing the input diode bridge with active devices. In this case, the switches from T1 to T6 has to be rated at 1200 volts. Why we are talking about bidirectional converters? This is very important. It's a new trend since there is the smart grid and there is a vehicle-to-grid capability of the converters more and more requested. So we need to reverse the energy from the battery to the grid, in addition to charge the battery from the grid. So the bidirectional function is more and more requested, and I would say is the selection choice for any new development for the range between 20 kilowatts and up to 350 kilowatts, for example. There is also the enabling of the standard full bridge boost converter, which is based on SiC topology, thanks to silicon carbide MOSFETs reduce switching losses and reduce sides. So this is what's new thanks to the silicon carbide technology, the full bridge boost converter. So let's give a look at an example, an exercise that we did with the demo solution, a demo board. So we use a specification in the table, so 400 volts DC in the input, 800 volts DC on the output, 13 kilowatts up to RMS, up to 15 kilowatts of peak power, a switching frequency of 70 kilowatts, and for the PFC design, we use a ripple current of 2.5 amps on the input with 10 volts peak to peak on the output as a ripple voltage. The equation for the design are shown there, and of course we can see that in order to select the design, the input inductor, we have to know the switching frequency as well as the ripple current that we can accept, and the modulation index of the converter, which is defined as the ratio between the input voltage and half of the DC output voltage. The RMS current is defined as the DC power divided by 3 times the input voltage RMS, and this will be the RMS current of the select inductor with a peak value of 25 amps, more or less. This bidirectional structure demo board is able also to be operated also as bridges 3-phase or single boost 3-phase solution when we disconnect the 3-level T-type cell. So we can evaluate the board and the system not only as a 3-level solution, but also as a 2-level. A very short summary of performance compared the 2-level and 3-level converter in terms of semiconductor technology is shown here, where silicon carbide is always performing better than IGBTs, except a very, very small frequency span at a very low frequency. But once we increase the switching frequency above 50 kilohertz, the difference between the two converters in terms of efficiency can reach up to 3–4%. So why selecting one solution against the other? Which are the pros and cons of the 3-level versus the 2-level? For the 3-level, we have losses distributed over more components, so we can spread better the heat generated by the switches. We can have higher higher efficiency at the higher switching frequency, thanks to the 3-level approach, and also thanks to the reduced voltage, we can reduce the volume of the input inductor. Which are the cons of this solution? We need more components. We have higher complexity also in terms of control. We could need an output voltage balancing for the split capacitor output, and also an expected higher cost because of more components. So in the table, you can see how many PWM complementary we need for the 2-level and 3-level converter. It's more complex. We need more gate driver. We need also more isolated DC-DC converter to supply the gate driver. This is the basic schematic of the solution. It's based on digital standard microcontroller, industrial microcontroller STM32G4, and is implementing the bidirectional functionality thanks to the grid relay, which are able to connect and disconnect from the grid. The system is based on a very simple control, both for the AC, DC, and DC to AC conversion based on DQ axis transformation. So we can decouple exactly the active and reactive power, and then we can have a very accurate regulation of the active and reactive power, as well as the power factor of the system. So this is a summary of the specs of the board. And the goal is to have a power factor higher than 0.9%, starting from 20% of the load, and the total harmonic distortion below the 5%, which is basically according to the standard, and an efficiency higher than 97%, starting from 20% of the output load. Key products are starting from the microcontroller, silicon carbide MOSFETs, and of course, there is one key component, which is not a semiconductor, but is a magnetic. So the input inductor, which is not trivial to manage, is not trivial to design, and is not trivial to manufacture with a reasonable cost. To give you an idea of the complexity of the system, the MCU is using high resolution timer to manage the high frequency operation, and is also equipped with math accelerator, like the Cordic for the trigonometric function, which is requested by the DQ axis transformation. Here is a picture of the system. We are the 3 input boost inductor given by Würth. This is a system that has been developed in partnership with Würth Elektronik, and we have developed and optimized this kind of components. Thanks to this, we were able to reach very high efficiency. So as I said, above 97% after the 2 kilowatts, and then up to 98%, and in that range for the full range. In terms of power factor, we are always in the range of 99%. So going back to the PFC inductor, which are the main requirements of this part, which is not semiconductor, but is impacting the performance of the system, not only in terms of efficiency, but also in terms of total harmonic distortion and power factor controllability. We need, in addition, to have low thermal resistance because of thermal management. We need low parasitic capacitance in order to have reduced losses on the components. It is able to work in offline application with very high voltage, and has to be low leakage, low radiated magnetic field with a compact design and easy to be mounted on the board. This is these are the main specs of the inductor that we use and has been optimized. And this is the final stage of a study that we did, starting from standard right core, so the EE65 and the EE80, which are able to manage the 27, 28 peak current grid, and we finalize with the toroidal one. And in order to give an explanation to this selection, we of course gave a look also at the cost of these final components. And if we took the cost of the EE65 core, but that was unfortunately able to handle only 17 amps, we finish with the 0.72% of the cost with the toroidal one against the 3.85 with the EE80. So we can understand which is the component of selection for low-cost industrial solution. So let's go to the conclusion. Charging stations are emerging application, and DC charger are gaining a market up to 50 kilowatts in terms of application. Of course, this is a basic building block of the final application, and we can stack several modules and interact them to have a very high power charging station. The bidirectional functionality is more and more requested in order to allow this converter and in general any battery charger with a smart grid equipped with the V2G functionality. The front-end converter represents the connection to the grid, so it's a very, very important part of the system. So even if it's simple, it has to manage the most difficult part of the game. silicon carbide MOSFETs is introductive, a very important factor in this application, allowing simple solution, simple architecture to be used with very high frequency solution and high performance in terms of efficiency and switching frequency, which is very, very important in order to have superior performance also in terms of power quality. Thank you for your time, and I'm ready for your question.
Thanks a lot, Francesco, for your interesting presentation. Now we would like to turn our attention to your questions, and we will wait a second until some questions will come in. And I already see one first question, Francesco. Can the Vienna converters be realized for low voltage applications, or all they are confined to only high voltage applications?
In general, Vienna rectifier can be used even for low voltage application. It depends on the input voltage as well as the output voltage. The main benefit is when you have high voltage on the output, so you can split the output voltage, you can divide it at least by 2. The output voltage, so this will allow to have reduced switching losses. There is also let's say, a decision to take, in consideration of the power that you have to manage. So basically, the specs has to be considered, not only the voltage on the output, but also the input voltage and the output power itself.
Perfect, thanks. Maybe one next question. Is the board suitable only for silicon carbide MOSFETs?
As I've shown, there is also a possibility to use other semiconductor technology, so superjunction MOSFET, as well as IGBTs. And for these different technologies, some fine-tuning for the switching frequency has been done. For example, for IGBTs, in order to have a best performance, the switching frequency should be reduced a little bit, maybe around 30 kilohertz.
Perfect, thanks. And maybe one last question. Is the board automotive grade qualified?
The system is just a demo board and has been built using industrial grade components. But in terms of concept, we have all the components available to have the same solution based on automotive grade components.
Thanks a lot. Thanks a lot for answering the questions. I would say if there are any questions left, we will answer them via email afterwards. So thank you very much for your attention, and I hope you enjoyed our presentation. The next and last presentation for today is case study how ESD could generate electromechanic issues, and it will start at 5 p.m. See you there and enjoy our digital days. Goodbye.
Thank you to all. Have a nice afternoon. Bye.